Hello and welcome back. We were looking at work in the previous lecture. So, we looked at how to calculate the work when you have displacement work of this kind. For example, when you have a piston which moves, we said that if the movement of the piston is fully resisted, at the same time there is no friction, then the work is given by integral of P dV. We discussed that work was a path function where depending on what path you take to go from one state to another, the work would be different. And we calculated this integral of P dV for various processes in the previous lecture. So, we saw that most processes can be given by some general form of PV to the power n equal to constant, which we called as a polytropic process. We saw various special cases of it. So, when n is 0, we have an isobaric process. When n is plus or minus infinity, we have an isochoric or constant volume process. When n is equal to 1, we have PV equal to constant, which for an ideal gas would be an isothermal process. And we saw that when you have an adiabatic process, you have n is equal to gamma. And for the general cases, we found out the value of this, where we got the work in terms of some constant pressure into difference of volumes, whereas P is a constant, which is an isobaric process. We found the work is 0 when you have a constant volume process. We found the work in terms of a logarithm of V2 by V1 for an isothermal process. And for the general case, we got an expression of this kind. All of these refer to, of course, only the displacement work when you have, for example, a piston cylinder arrangement, or you have some volume which is deforming, and because of the change in the volume itself, we have work which is done, and this kind of expression gives the work in those cases. We will go on to a few other types of work, but before that, I thought we just look at a few questions to see how well we have understood what we have done so far. So, what I would like you to do is to read the question, pause and think of the answer for yourself, and I am going to discuss it anyway. And if you haven't quite understood how I get this answer, maybe this time to review what we have done so far, or maybe ask questions on the forum if you are not able to follow. So, the first question is, what is the cyclic integral of a property? Of course, by the cyclic integral, what we mean is what is the value of a property when we go in a cycle. So, for example, I can look at any diagram, and I am going to look at a PV diagram. Let us say I start from point 1, I go to some other point 2, I go to some other point 3, I can go to some other point 4, and then some 5, and then some other 6, and then some other 7, and come back to 1. So, if I wanted to find out the cyclic integral, so if I find out, for example, the way we represent it is this, the cyclic integral of a property. So, if I take some property, for example, volume, how much is this? Or if I take along this cycle, so going from 1 to 2 and 2 to 3, 3 to 4 and so on, if I find out some other property, how much is this? So, essentially this would be the change in volume from 2 to 1 plus change in volume from 3 to 2, from 4 to 3, from 5 to 4 and so on. And if we add up all of those, what do we get? So, you should possibly pause here and try to figure out the answer. And the answer, of course, is 0, because it is a property. So, if you come back to the point where you started, at point 1 the temperature was, for example, T1, the volume was say V1. When we come back to the same point 1, the volume is still V1, the temperature is still V1, T1. So, the difference between the first point and the final point is T1 minus T1, which is essentially 0, and same with volume and so on. So, we see that if you have any property, because it does not depend on the path you take, as long as you come back to the same point, the value is the same as it was where we started off. So, if we find the difference and integrate, we would get the value as 0. Which now brings us to the second question, what is the work done in a cycle? So, we can look at the same kind of a cycle, maybe just for simplicity I will make it with a fewer number of processes. Let us say I draw something like this. I go from 1 to 2, 2 to 3, 3 to 4 and back from 4 to 1. So, what is the cyclic integral of work, or what is the work done in this cycle? So, what we are trying to find out is this quantity. So, again maybe it is a good time to pause and think about what this value is and then look at what we get. So, one of the things we see is that this value is not 0, which is possibly the most important thing to note at this point. So, this is not 0. So, we start from this point 1, go to 2, go from 2 to 3, 3 to 4 and 4 to 1. We ended back at the same point where we started. The pressure, cyclic integral of pressure would be 0, cyclic integral of volume is 0, cyclic integral of temperature is 0 and so on. So, all of these properties the cyclic integral is 0, but for something like work, which we see as a path function, it depends on how we went from point 1 and came back. So, what we see is going away from point 1, we went from here to some 2, went from 2 to some other 3. Coming back, we did not go back along this line. We came back in some other process, and therefore, the cyclic integral of work is non-zero. Since we went away from one along some path, came back in some other path, what we see is these paths enclose a cycle, and what we know is that if the work is only in the form of displacement work for a system as we were looking, then the work in general is given as integral of PdV. So, we can integrate this over all the processes. So, the cyclic integral of del W would be integral from 1 to 2 PdV plus integral from 2 to 3 PdV plus integral from 3 to 4 PdV plus integral from 4 to 1. So, we can actually look at these areas. From 1 to 2, this integral would be the area under this curve on the v-axis from 1 to 2, which is essentially this area. The integral from 2 to 3 is the area, let us mark it in some other color, between 2 and 3 along this axis, which is essentially this area. So, we sum up those two and then integral from 3 to 4. So, we see from 1 to 2 the volume is increasing, from 2 to 3 the volume is increasing, the pressure is always positive, we are dealing with absolute pressures. So, this quantity is positive, this quantity is also positive. From 3 to 4 we see that the volume is actually reducing, because the volume at 4 is the volume at this point, which is less than volume at 3, which is the volume at this point. So, this quantity is going to be negative, and similarly the pressure at 4 is greater than the pressure at 1. So, going from 4 to 1 we see the volume is again reducing. So, we see that these two quantities are going to be negative, whereas the first two quantities are positive from the way in which we have drawn this. So, we still have to find out these two values. So, going from 3 to 4 is the area under this curve, and going from, this is 4 to 1, we see that that is the area under this curve from 4 to 1. which is essentially this. So, what we see is that we have added the brown areas and the red areas, we have subtracted the light green areas and the dark green areas, and the net work, which is the work done in the cycle, is what is left over, which is essentially the area enclosed by the cycle. So, we see that the cyclic integral in this case is essentially this area over here, area enclosed by the curve. So, when you have a closed curve of this form, the area enclosed by the curve on the PV diagram gives us the net work done, which as we see is not 0 because this area has some value. So, even though when you go in a cycle, the properties, the cyclic integral of the properties become 0 and the properties remain the same when we come back to the initial point, what we see is that the area does not become 0, which means we have done some work in going about the cycle and coming back to the point where we started from. So, we came back to the initial point, but in going around and coming back, we did some work, we expended some work in this process. So, that is something which we need to keep in mind. Of course, the third question which I have here on the slide is fairly easy. The question is, what is a polytropic process? And since you have covered this, you possibly know it, but you might want to pause for a moment here and recollect what it is. And once you have done that, you should be able to get something of this form. So, we have some curve of the form P v to the power n equal to constant or P specific volume to the power n equal to constant. We are looking at systems. So, the mass is constant. So, if I divide this by mass on both sides, there is some different constant, but I get v by m to the power n, which I can multiply on the other side, and I get a constant here. So, both of this should be all right. So, if you have understood this, we will go on to a few more conceptual things of this kind, just to ensure that we have understood this stuff properly enough before we go ahead. So, what we said is that we defined work in terms of some interaction between a system and its surroundings, and we said that the sole effect should be able to be reduced to the lifting of a weight. So, what we see is that it is an interaction between two systems or a system and the surroundings. So, therefore, we require a donor, somebody to do the work, a receiver, somebody to receive the work, and some interaction between the donor and the receiver. So, we need all these three aspects in order to define work. So, we need somebody to do the work, something on which the work can be done, and there has to be interaction. So, if you just have the two objects and there is no interaction, then of course, there is no work which is done. So, in this fashion, what we can see is that the work interaction for the system plus the work interaction for the surroundings, if you sum them up, they have to be 0. If there is only one system which is doing work on the surroundings or the surroundings is doing work on the system, if you sum up the work interactions for the system and the surroundings, then the sum has to be 0. In the same line of thought, if you have many systems which are interacting with each other, so some are working on the others, some are working on the surroundings, each of them is doing work on its surroundings, but if you look at say systems A, B, C and the surroundings ignoring A, B and C, so if you look at the work interactions for all of these put together, the work for system 1 and system 2 and system 3 and so on up to the nth system, and then one of them is of course the surroundings of all of the others, and the sum of these also has to be 0, okay, because any work which is done has to be either from one system to another or some other third system to a fourth system or so on. So, if you add all of them put together, they have to be 0, and in order for work to be done, the process must be resisted by what is getting the work, and therefore, there must be resistance from the surroundings. Only in that case we can have work which is done. So, if there is no resistance, it is like the other system is not accepting anything. So, in that case there cannot be any work done. So, we will just look at one or two examples to see if you have understood this. So, of course, from Newton's law in SI units, we have F is equal to ma. Some of the things we need to remember is at equilibrium, sigma F is equal to 0, all the forces are balanced. So, we are looking at systems which are always in equilibrium or very close to equilibrium. So, in all of these cases the forces must be balanced. If the forces are balanced, there is always resistance, because you push some force and try to move something, the force is in balance, or it is almost balanced, which means the object cannot move fast, it is resisted, it can move very, very slowly. So, only in these cases we are considering work to be done. Second thing is, you have to remember, just because the forces are 0 does not mean velocities are 0, because force is 0 just means acceleration is 0. We are considering constant masses. So, if the force is 0, it means acceleration is 0, but does not mean the velocity is 0. So, you can have the object moving at a constant velocity along a straight line, the velocity can be non-zero, but the forces can still be 0. And third thing is, of course, that sigma f, the net result of all the forces, is approximately 0, but that does not mean that the work is 0. So, our forces are always close to equilibrium, which means that if you sum up all the forces, they must be approximately 0. Of course, what we are saying is we are near equilibrium, we are quasi-static, so we can have slight imbalance of force, because of which we are having some work which is done, but the work itself is non-zero, even though we are close to equilibrium, and our equilibrium condition is that forces are 0. So, this is something which often gets missed out. So, our work interaction is non-zero, but we are close to equilibrium. So, our sum of all the forces is approximately 0 all the time, because only under this condition is the work resisted, or the forces are resisted, and only when there is resistance we can have work which is transferred. And what we will see is that work and heat are modes of energy transfer. We have defined work so far. We will look at heat in the next lecture or so, and we see both of these are modes of energy transfer, and which form of energy is transferred, whether it is in the form of work or in the form of heat, depends on the system which we are using. So, we will see that depending on how we choose our system boundaries, the energy transfer can be in the form of either work or heat, and we have defined work so far. Once we define heat, we will come back to this and see how changing our choice of the system boundary. So, we are usually drawing some system boundary. For example, we have a piston cylinder system, we are saying our system is whatever is here. This is our system in general, for example, whatever is inside this. So, we can draw different kind of boundaries in different cases, and we will see that whether it is work or heat would depend on where we draw this boundary and what kind of system it is. So, I am going to ask you another little question to think about before we go forward. So, there is a tree, let us say there is Newton sitting under this tree, and we have an apple falling. So, let us say we consider this apple from the time it is on the top of the tree. So, just before it hits Newton on the head. So, it does not really hit. So, it goes from somewhere here to here, and it has not touched Newton yet, but the apple is falling, it has fallen. So, it has travelled some distance, and let us say that distance which it has travelled is about 1.5 meters. The mass of this apple is say 0.05 kilograms, and the acceleration due to gravity is 9.81 meters per second square. So, the question is, what is the work done, or what is the work interaction for this apple when it falls from this point on the tree till this point. So, let me just mark that maybe in some other color. So, when it falls from this point over here up to this point over here. So, what is, let us say this distance is 1.5 meters. So, what is the work interaction for this apple? So, I would again suggest that you pause the video here and think of this question for a moment and try to find out what the answer would be. So, if you have thought about it, let us also maybe make one assumption which is not mentioned here. Let us say any resistance due to air, drag due to air, let us assume that to be 0. We are assuming essentially that the air does not have any viscosity, or that any effects due to viscosity on this apple are negligible. Okay. So, that is another assumption which you may want to take into account, and you can think about it again for a few moments and pause, and then I will tell you what the answer is. The answer of course is 0. Okay. So, we have the apple which is falling. The apple has moved. It was at some location earlier, it is now at some other location. It moved, but there was nothing to resist its movement. So, if we assume that the viscosity effects are negligible, then there is nothing to resist the movement of this apple. So, therefore, there is no work which is done. So, we have a system which is the apple. It is moving, but there is nothing to receive energy. So, the donor, potential donor is the apple, it can donate energy, but there is nothing which is there to receive the energy. So, if nothing receives the energy, there is no resistance to its movement. So, the apple will keep falling, it will keep accelerating as it falls. So, as long as we are considering that it has not hit anybody and given energy, the work done by this apple is 0. So, the work interaction for this apple would be 0 in this case. So, the kind of process, for example, the apple falling and other processes of this kind are actually, there is no resistance. So, they are not quasi-static. So, the apple is actually accelerating, but we can also think of other processes which are non-quasi-static processes. So, one of these examples would be a membrane separating a vacuum. So, if I have, for example, two chambers, a chamber of this kind. So, I have a rigid chamber, and in between I have a membrane. One side of it, the pressure is 0, I do not have any mass, nothing is there, so that is vacuum. The other side of it I have a gas, and they are initially separated by a membrane here. I have some gas at some pressure P. So, if I puncture this membrane, so the gas from here will flow and occupy this space. So, again in this kind of a process, the work interaction would be 0. So, we see that the volume has increased. This gas was initially occupying some volume V1, let us say this volume is V2. So, the initial volume of the gas was V1, the final volume for the gas is V1 plus V2. So, the volume has increased, but what we see is that there is no resistance for this gas to flow and occupy this volume, plus there is nothing here on which it can, to which it can give or get work from. There is no recipient of any work which this gas could have given. Therefore, in this case also the work must be 0. So, when this gas expands from here to here, so in the work interaction must be 0. So, this kind of thing is essentially what we call as also unrestrained expansion. This is a case of completely unrestrained expansion. You can also have partially restrained expansion, where there is some resistance. So, for example, if the pressure here was high, the pressure here was low, and you allow this to expand, it is not completely resisted, it is only partially resisted. So, that kind of case also the work done would not be given by completely P into change into volume, it is only partially resisted. A similar case would be free fall. We already saw this in the case of the apple. So, I have another example here. So, let us say there is somebody who is jumping from a plane, he has not yet deployed the parachute. Let us say that the person has very little air resistance. Okay. So, area is very small, there is no resistance because of air, the person is falling and accelerating as the person falls. So, during this free fall, the work interaction of this person would be essentially 0. Of course, the person does have some area, but the area perpendicular to the air is perpendicular direction of travel is extremely small. So, this would be at least approximately equal to 0 in this case. Let us say now the air is fairly dense, or then what you see is that there is some amount of resistance to air flow, and you have some amount of work which is being exchanged or being done. So, for example, let us say this person has a mass of say 60 kg. So, the person's weight would be essentially mg, which is 60 into 9.81. since I am not using a calculator at the moment, I am going to assume this to be 10, which is approximately equal to 600 newtons. So, if the person just falls freely without any resistance, the person is accelerating. So, gravity is in the downward direction, the person is accelerating, but any work interaction is 0. Now, let us say the air offers some resistance to falling. So, let us say the air offers a resistance of say I do not know any value, let us say 50 newtons. That is the force which is resisting the person falling because of area and viscosity of air. Let us say if there was a resistance of 50 newtons and the person's downward force pulling the person down is 600 newtons, then any work done is only because of the difference in the forces. So, if this was 600, then the imbalanced force is about 550 newtons and the balanced force is only about 50 newtons. So, if this person fell by say 10 meters, then any work would be only because of this force of 50 newtons. So, any work done, if the person fell by say 10 meters, the work would be about 500 joules. 50 into 10 meters would be 500 joules. So, this part is unresisted force and does not do any work. Now, the person deploys the parachute and the person is drifting slowly. So, the parachute is completely deployed. The person was initially traveling fast. Once you deploy the parachute, go down slowly. So, the parachute is making sure that the person does not accelerate, make sure the person goes very slowly. Then the person will be drifting, not accelerating. So, you can have a full resistance now. So, the weight of this person is 600 newtons, which is pulling him down. Because of the parachute and air resistance, the parachute is completely taking care of providing resistance so that the person is not accelerating anymore. In this case, whatever is the distance travelled, if the distance travelled is say h, then the work would be mg times x. So, it is essentially 600 into whatever is the distance. So, if we travelled like say 10 meters like this, then the work would be 6000 joules, which is essentially 6 kilojoules. So, over here there is no resistance, so the work is 0. Over here there is partial resistance, whatever is the amount of resistance which is there, corresponding to that we have work which is done. In this case this is fully resisted, and so corresponding to the entire force we have work which is done. So, this is how we see that there can be unresisted, partially resisted and fully resisted processes. In unresisted processes there is no work interaction because nothing is accepting the work. In partially resisted processes we have some amount of resistance. So, the surroundings is accepting some amount of work. So, only to that extent work is done, and in fully resisted processes there is resistance to the complete force, and therefore, all of that force is taking part in doing some work interaction. So, this is something which we see.